Hello, my good friends. Today I want to talk about common logarithms. So get yourself a paper and a pencil because when you're thinking, you should be writing, and as you're writing, you should be thinking. And let's begin. So if you recall from way back in elementary school, we use a base 10 numbering system. So, for example, if I were to write down the number 52,741, it would look something like this, comma in there. And then let's talk about the place value of these things. The position of the number tells us the actual value of the place. So if you remember, you did something like this where the 1 was in the ones place, the 4 was in the tens place, the 7 was in the hundreds place, 2's in the thousands place, and 5 is in the 10,000s place. But since we use a base 10 number system, let's talk about that in terms of exponents. This would be 10 to the 0. This would be 10 to the first. This would be 10 to the second, right? Because this is 700s and 10 squared is 100. This would be 10 cubed, and this would be then 10 to the fourth, and we could go on and so forth like that. So we use a base 10 number system. A common logarithm is simply a logarithm that is base 10. So remember, a logarithm asks what's the exponent on a base that gives a power, and if you're dealing with common logarithms, it would be base 10. So if I were to write the common logarithm of a number, say like what is log base 10 of 100, I wouldn't even write the 10 in there. Now for simplicity's sake, if you want to help yourself out and maybe write a 10 in there so that you can see the base, because it helps you think about it, that's fine. But ordinarily, you don't write the base in there for a common logarithm or a logarithm that's base 10. So this question right here is asking, what is the exponent on 10 that gives me 100? And that exponent is 2, and that's because 10 squared is equal to 100. But what if I were to do a power that's not a simple or easy exponent of 10? Let's say, what if I wanted to do this? What if I said log of 150? Now, that question is asking 10 to the what is equal to 150. Well, 10 squared is 100. I know that 10 cubed is 1,000, and 150 is in there someplace. So logically, wouldn't the exponent have to be something between 2 and 3? But we don't have an integer value. You'll have to reach for a calculator. So if you've got a scientific calculator, a TI-83 or TI-84 or something like that, reach for that. And you'll notice that there's a button on the TI-83, 84 series, and that's the one that I'm going to be basing this off of. You have a button that is next to the 7. Okay, so it says log, and if you just type that in there, type in log, it should open up parentheses, and then I'm going to type in 150, and I'll close the parentheses, and I get an exponent of 2.17, and I'll go to 4 decimal places, 61. So that is the exponent then on 10 that would give us 150. And let's try it. Let's take 10 to the 2.1761. And that makes sense because we expected a value between 2 and 3. And since 150 is perhaps pretty close to 100, maybe a little closer to 2 than it would be on 3. But type that into your calculator then as a separate problem. 10 raised to the 2.1761, enter. I'm getting 150.003019. So yeah, that works. Why isn't it exact? Well, because it's rounded. So that then would be my answer. So we can use these now the properties of logarithms here, of common logs, in order to solve equations, exponential equations, where the base does not give us an easy answer for the power. So for this one here, solve 5 to the x is equal to 100 or equal to 50. Well, 5 to the first is equal to 5. 5 squared is equal to 25. 5 cubed is equal to 125. Well, 50 is between 25 and 125, so my exponent has to be somewhere between 2 and 3. But I don't have an integer value, so what do? Well, I could take the logarithm of both sides. So what does that do for me? Well, let's do the logarithm, common logarithm, so it's base 10, log of 5 to the x, and that has to equal log of 50. Now, this does not mean log multiplied by 5 to the x. It's not log times that, even though we are using parentheses. Logarithm is like an operation. So now that I've got it in in logarithm form, I can use the properties of logarithms now to get that exponent there of x out of the exponent and bring it down as a multiplier. Remember that, properties of logarithms, the power property? This now becomes x multiplied by log 5. And of course, this one is log of 50. Okay, now how do I undo multiply by log of 5? Well, I will divide by that. So I'm going to divide the entire left-hand side by log of 5, and I'll divide the entire right-hand side by log of 5. This will cancel, and the other side does not. My answer here is going to be x is equal to log 50 divided by log of 5. And you're tempted probably now to cancel the logs and just maybe get 50 over 5. But that's false. Log isn't a number that it can be canceled like that. The question's saying the exponent on 10 that gives me 50 divided by the exponent on 10 that gives me 5. Those are two different numbers and they don't cancel by division. You can't even cancel the 50 and the 5 and call it a single log of 10 or something like that. These are individual things and they don't cancel by division. What I would have right now if I didn't have a calculator is I would have my final answer. That would be what's called a calculator-ready solution. Calculator-ready solution. It's ready to be put into a calculator. And since I've got one, let me go ahead and type it in. So I'm going to type in on my TI-84 now, log, and it opens up parentheses. I would say 50, and then I would close the parentheses and then divide by, press log again, and say 5, and then close that parenthesis, and I get an approximate answer of 2.4307. So what is the exponent on 5 that gives me 50? Okay, well, it's 5 to the 2.4307. That's what gives me approximately, no, it's not exact again, approximately 50. Try it, you'll see. So what we're going to do is we're going to take the logarithm of both sides of an equation where the variable is in the exponent. That allows us to move the variable out of the exponent as a multiplier. Okay, so now here's one that's a little more challenging. Solve 3 to the 2x plus 1 equals 12. Okay, so the first thing I'm going to do is I'm going to take the logarithm of both sides, the common log, log base 10 of 3 to the 2x plus 1, and that has to equal log of 12. I can't pull the exponent down as a multiplier until and unless it's a logarithm. So now I take the exponent and I bring it down. This is now going to be 2x plus 1. The group of that times now what remains, log of 3 equals log of 12. Now I'm going to divide both sides by log of 3. Divide by log of 3. This whole package here will cancel because that's the number on 10 that gives me 3, or the exponent on 10 that gives me 3. But I can't cancel the logarithms on the left, nor can I cancel the 12 divided by 3. That stays put. So what I get is 2x plus 1 is equal to log of 12 divided by log of 3. Now, I'm going to continue to solve for x by moving the 1 to the other side. So that's going to be, say, a minus 1 here and a minus 1 here, and those cancel. So I get 2x is equal to log of 12 divided by log of 3 minus 1. And then I'll divide this side by 2 to cancel there. And I could do a big, long division thing like that. That's a little awkward. Isn't dividing by 2 the same thing as multiplying by 1/2? Yes, it is. So I could say 1/2 times that whole group right there. And that would be my calculator ready solution. And then I can say in the end, well, x is approximately equal to, now I'll do all of this kind of one step at a time. I'll do log of 12, close the parenthesis, divided by log of 3, close the parenthesis, equals, I get 2.2618595. Then I'm going to subtract 1 from it, equals, I get 1.261859. And then I'm going to say then divided by 2, or you can multiply by 1/2. So I get approximately 0.6309. There's my answer. Okay. All right. Now let's talk about, gee whiz, what if I don't have a base 10? Well, there's something here that we're going to call the change of base formula, right? So the following formula is used to exchange expressions with different logarithm bases to common logarithm expressions. So the change of base formula allows you to take a logarithm that is not base 10 and make it into base 10. And this is how you would do a calculator problem up until recent years. It used to be a scientific calculator only did 2 kinds of logarithms, base 10 and then the natural logarithmic base, which will be for another lesson. So if you didn't have either one of those bases, let's say that you had, I don't know, base 5 or something like that, you had to convert it into base 10 or convert it into base E, which is the natural logarithmic base using this formula. But here's the basic principle. It says if I have a log of some base A of some power n, I can convert that into a fraction of 2 different logarithms. Log of a new base, I wrote the B instead of log because that's the base. Log base B, the new base, of n divided by log new base B of A. So I have, the thing to notice here is the A. The A is down low, right? The A has been dropped, it's the base, so that's the thing that goes underneath in the denominator. And then the N is the one that goes up here in the numerator. And notice my bases change from base A to both of these then being base B. So here's an example. So let's say that I would do something like log base 5 of 12. Gee, I don't know how to do that on the calculator because I don't have log base 5 as an option. I only have log base 10. If you have a TI Inspire, you actually have a way to type in a base. It'll do bases other than 10 and E. But anyway, here's how this would work. I would make it a fraction of a new base. Log base 10 of 12 divided by log base 10 of 5. And then I can do that on the calculator because I've changed them. Instead of base 5, I've changed it into base 10. So log base 10 of 12 divided by log base 10 of 5. I get an approximate answer of 1.5440. And so that would then be 5 to the 1.5440. That would be what should give me approximately 12 then as the exponent on 5. Now, here's a problem. Some students want to come in through here and they think, oh, it's log of this divided by log of that, so the logs can cancel and I'm just left with 12/5. That's false. Okay, that's not true. No. Some students want to do something like this too. They'll see something like log of 12 divided by log of 4, and they'll want to say, oh, the 12 and the 4 will cancel, and so that just leaves me a single log of 3. That's also false. Okay, you cannot cancel logarithms themselves, and you can't cancel even the arguments of logarithms individually, because it's not 12 divided by 4. It's the exponent on 10 that gives me 12 divided by the exponent on 10 that gives me 4. Okay, so for this one here, express log base 8 of 15 in terms of common logarithms, then round to the nearest decimal. All right, so I don't want base 8. I'll convert it into base 10. This would be log base 10 of 15 divided by log base 10 of 8. Try that on your calculator now. See if you get the same thing that I do. I get approximately 1.3023. Does that make sense? Does that mean that 8 to the 1.3023 is somewhere close to 15? I think so, because 8 to the first is 8, and 8 squared is 64, so that's, you know, pretty close to somewhere in the middle there. All right. Well, that's it for today. May your day be merry and bright, and may all your mathematics be right. Talk to you later.